Good afternoon, everybody. So what we are going to discuss today is to continue our discussion on applying Newton's second law. Newton's second law. And in particular, I want to talk a little bit about the centripetal force and how to relate the centripetal force using centripetal acceleration. Some of the comments mostly has to do with the box and pulley problem. There's some question regarding the circular motion, and I want to talk about the circular motion with this pre-lecture question, along with the rotating barrel of a ride that you see in the state fair. So we will talk about that at the end of our discussion. First, we want to solve more Newton's second law problems. Okay, so without further delay, let's take a look at this particular checkpoint question that you have already done. I believe this was on Tuesday's class, Tuesday's checkpoint. So we have this box that's sitting on the inside of a moving truck. The truck is accelerating to the left with a acceleration A, and the box is accelerating together with the truck. Okay, so the box is relatively at rest to the truck. So in what direction do you think the static friction acting on the box is? First of all, do we all agree there has to be a friction on the box? Should C be correct in the sense that there is no force in the horizontal direction on the box? So what do you think about C? What if someone said, since the box is not moving relative to the truck, it seems at rest to me, then there is no force acting on it. Is that correct? Anybody? It's not correct. Yes, thank you. Would you like to elaborate a little bit more on why that is not correct?
Even if there's no net force when the box is relative to the truck, there's still different forces that are acting on it.
So there's the gravity, yes, we do still have the gravity and the normal force, and anything should be on the horizontal direction. Is there any force in the horizontal direction? So what do you think the box acceleration is? Is it A or is it 0? It's A, yes, along the same thing with the truck. The truck is moving together with the box, right? If the box has acceleration that's not A, if the box and the truck will not be moving together. Because they're moving together, the box must also have an acceleration. If it has an acceleration, it must have a force to provide that acceleration. So they must have a force pointing to the left now, which is correctly indicated by choice A. Okay, and that force is provided by static frictional force. Now this is very interesting. Sometimes to think about which way the static friction force is pointing at can be confusing. So how do we figure out the direction of the static friction? In this case, we know that straightforward from the direction of the acceleration is to the left. But you can also try to think about this using in what tendency is the box trying to slide off? Because, okay, once the truck starts accelerating, now relative to the truck, the box has a tendency of trying to slide backwards, right? The box is trying to slide to the right-hand side, but it is not, which means the static friction prevented that tendency to slide off. So the static friction is pointing to the left, providing the acceleration of moving the box along with the truck. So you can see that if you use Newton's second law, it becomes much more straightforward to think about which way the static friction should be pointing at. Okay, pointing in the same direction as your acceleration. So it's A. Okay. So when we say static, meaning that is not moving, we only meant it's not moving relative to the surface, but the surface and the object could all be moving together relative to the Earth's reference. Okay, so remember we said we previously solved the tension, we solved a problem involving the ramp, also with the spring. Now let's look at a very common type of problems that's showing up involving the pulley and the tension in the pulley. I want to start using this checkpoint question, but we're going to break it down into multiple steps in order to answer this question. So this question you have done, one case you have mass 1 hanging down, and mass 2 is pulled by mass 1 and they're threaded by the pulley. There's no friction between mass 2 and the table. So when you let go of mass 1, they simply all moving, accelerating down. And in this case, we're going to call it A1, they're accelerating down. And if there's some friction between mass 2 and the surface, there is another type of acceleration with mass 1 and 2. We call it A2. And there's tension inside the string, right? So here's the tension, you have your tension, here you have your tension. In which case is the tension in the string biggest? So this, at first sight, it seems very complicated. So I'm going to break it down into many little steps. So each of these could be a little problem by itself. So first of all, let's simply look at this situation that with no friction. Forget about case 2, we're only going to look at case 1. And this is also the same drawings on your handout. Well, the handout is a PDF file that I uploaded into the weekly folders. It has this particular problem in it, but you can also just look at my drawing right here. So if you only have this situation without friction, let's first tackle, we're curious about the tension in the string, right? So let's first tackle what's going on if nothing is moving, if they're both at rest. So let's start with this particular clicker question that you put a little stop here, so nothing is moving. M1 and M2 are at rest. So now if I ask you, what is the tension in the string, what would you answer? I'm gonna go ahead and start the pull. While people are putting their voting, I see a question from the chat. Is the test curved? I want to say that individual tests are not curved, but the final grade might be curved. So once I get the final grade distribution, so it's like 10% from this, 20% from that, 20% from the test, and I put everything together, then I do my curving then, not the individual test, okay? Usually I never needed to curve the individual test. We'll have to see. Sometimes the online could be skewing how people do, but I never curve it in a way to hurt your grade. If there is any curving, it's only going to be in the direction that your grade will get better. Okay, all right. I'm getting most of the votes already. Are there any last minute vote? A few more seconds. Okay, okay. Now I'm going to go ahead and close this. This is our results, right? Yes, and this seems to be not taking too much time, seems to be straightforward. A is correct answer. Very good. So the tension in the string is, now if you isolate the object M1 and draw your free body diagram for M1, you have how many forces? You have F of G, gravity, and you have tension acting on M1, those two forces only. And since M1 is at rest, then tension must be equal to the gravity of M1, so which is mg. Tension F net equals M1A, tension minus M1G is 0, so tension is equal to M1G. So A is correct. Now what is happening to M2? The same kind of tension is pulling on M2. As we said, the tension is everywhere the same inside the rod. If on this side of the rope is the T, on this side is the same tension. So same tension is pulling on M2, but you have this little stop here. So there must be a force acting from the stop to M2 to keep it from accelerating, right? But that's not really what we're curious about here. We can focus on M1, we can find out what the force is inside the string. So A is correct. So we know how to do tension when nothing is moving. Well, if they're moving, there shouldn't be too different because we simply just need to change what the acceleration is. Here, the acceleration is 0, but once it starts moving, okay, so once now they start moving, let's simply just predict the tendency of change. Do you think the tension now is going to be bigger or smaller or the same as before as in mg? Just to remind you what we had previously, we did a free body diagram on M1. Tension here, we said tension minus, actually, let me do the other way around. I'm going to do downward as a positive direction. So I'm do M1g minus tension is M1 times the acceleration of 1. Okay, so this is the free body Newton's second law being applied on the first mass. So once the card is released, what do you think is happening to the tension? Again, I don't think this requires too much discussion. I will let you go ahead and vote right here. Okay, I've gathered most of the votes already. 5 more seconds. If you have last minute vote, please put it in. Okay, any votes? All right, I'm gonna go ahead and close the poll right now. And let's take a look at our results. So we have a little bit of a split between these choices. C is about half of the answer and A and B about the other half. Okay, so you may not be able to find the tension right away, but can we at least say, is it bigger or smaller than the number before? So when acceleration is zero, you can see when you make this go to zero, tension is equal to m1g. Now, if a is not zero, so a is now a number that's bigger than zero, right? So what is tension? Is it bigger now? If it is bigger than the gravity, we know that it cannot be m1g. Do you agree? If it is m1g, acceleration is zero, but it's moving. If it is bigger than m1g, do you think it can go down? Your force is upward is bigger than the force going downward. If tension is much bigger, then it's going to accelerate upward. And that is not the case here, right? So because it's accelerating downward, the only possible way is for tension is now to be smaller than m1g. So m1g is bigger. Actually, I can draw my tension to be a smaller arrow, but acceleration, gravity is bigger. So the net force is pointing downward and your acceleration is downward, right? So you can see C is correct. The tension now is smaller than what it was before, also smaller than the weight of gravity. Now let's go ahead and calculate what the tension is. If you have your handout, print it out, or if you just take your notes, your piece of paper, and try to work out what do you think? Can you calculate tension in this case? You see that in order to do tension, you need to know what acceleration is. So another question is, can you find the acceleration? And can you also find tension? Okay, I'm gonna give you a couple minutes to work on this within group, try to solve this problem together. And then I'll bring you back and I'll solve it together with everybody, okay? All right, so think about how you will calculate the tension when everything is moving together. Again, we're considering the no friction situation.
Do M1 and M2 have any values, or do we just leave those as variables?
Leave them as variables. So leave your answer algebraically. Even if you were giving values, I always recommend, it's a good practice in physics to not plug in numbers until the very end. So you're gonna work out the algebraic expression first.
Okay, thank you.
No problem. All right, so let's have a discussion within your group for a couple minutes on how to solve the tension. Okay, so people already came back. So I want to ask, in order for solve for tension, we need to know what the acceleration is. Anybody have solved for the acceleration or talked about it? And what are some thoughts? What can we do to find the acceleration of block one or the block two? Block one and two.
I think that the acceleration on mass 2 is the same as the acceleration on mass 1 because the problem says that the pulley is frictionless.
Excellent. That's a really important observation that one and two are connected by the not a string that cannot be extended. So they're all moving together. They're moving together, meaning that they have the same acceleration. Very good, Tristan. So that's important. This is the same one. So you label this as A here and A here, M1 and M2, the same A. You don't have to do A1 or A2. Very important observation. So they have the same acceleration. And then the next step is, how do we calculate this acceleration?
We take a look at all the forces acting on mass 2
Okay.
and then divide that by mass 2.
Starting with mass 2. Okay. The forces acting on mass 2. Okay, let's label the forces on mass 2. We have, I'm going to label the obvious ones, the F of G on mass 2, normal force on mass 2, and what else?
The tension.
The tension. Okay, so we need acceleration, we need tension, but we don't know what tension is. We're hoping to get acceleration first and then to get tension. So it seems to be, well, I don't know what tension is, so I couldn't really solve for the acceleration starting with mass 2. What do we do?
It's just gravity.
Just the gravity. And gravity of M1 or M2?
Just one.
Just M1. I think you're getting to a really important idea is what is responsible for them to move all together. So this is gravity for one. This is the tension. So I'm going to show you, first of all, a simple sort of shortcut solving this problem. And then I can show sort of a more nuanced way to do this. So to find, first, we want to find acceleration for the both of the masses. First, I'm going to show a short way to do this. What is the short way? The short way is what is responsible for M1 and M2 together. Because they're moving together, we can view them as one piece, right? They're both accelerating in the acceleration. So M1 and M2 are one piece. They are both accelerating with the same acceleration A. And okay, F net equals total mass MA. And what is a force that is responsible for accelerating both of them? And that is the weight of mass 1. Okay, weight of mass 1 is dragging mass 1 down and pulling mass 2 through the pulley to the right. So they're kind of along this direction, they're moving together. Okay, so mass 1 is the net force that's acting on the system. Here I'm viewing M1 and M2 as a whole. So I'm viewing this, I'm sorry, as a whole piece on the system. The system is M1 and M2 together, okay? All right, so you can see if I do this, I find my acceleration right away. M1G is responsible for accelerating both masses. The weight of mass 2 is not gonna help. The weight of mass 2 is balanced out by the normal force. It's not the force that's responsible for them accelerating. It's only the weight 1. So we got the acceleration, okay? And then you can find tension. But before I do that, let me show you the long way to find the acceleration. If you're not really convinced that we can view our motion in this way, that one is horizontal, right? one is vertical together, you can always do it separately. So if you do it separately, you need to apply Newton's second law, M1 and 2 separately. So you will apply Newton's second law 2 times. M1 and M2 separately. So let's apply it on M1. So on M1, you have 2 forces. Gravity minus tension gives you the acceleration times mass of M1. This is M1G minus tension equals M1A. Now let's apply Newton's second law on M2. I have only tension. Tension is the net force that's accelerating mass 2. So acceleration, so tension equals M2G. Okay, so I have one equation, two equation, 1 and 2. You can use 1 and 2 equation combined and plug in tension in here. So M1G minus M2A is M1A. So you did M1G is equal to M1 plus M2 acceleration. And again, acceleration is equal to M1G over M1 plus M2. So it's the same result as I did previously. This and this the same. Okay, all right. So when I view this as a whole, when I view M1 and 2 as a whole, tension sort of just become an internal force. It's inside the system. 1 and 2 and the strain combined is one piece. So you don't even think about tension anymore. Tension is whatever is inside. It's only the outside force that can accelerate the system, right? In this case, it's M1G. All right, so we have found, go ahead.
If we were to swap the axes so that the FG is technically negative and the tension is positive, would the summation, the M1A, be negative? Would we have to put a negative sign?
Now, if you want upward to be positive, then tension minus M1G is equal to acceleration is now also negative. So you put a negative sign here for acceleration and the result is the same. So you can see it still become M. So this result and this result is the same. So M1G minus tension is M1A. So no matter how you define your positive or negative axis, they get the same result. Does that make sense?
Yes.
Okay, all right, so you can define whichever direction to be positive, but just be careful with what is positive or negative with your quantity. So you can see that, okay, I found acceleration, the tension is easy. I can either use equation 2 or equation 1 now, right, to get my tension. So my tension would be, if I use equation 2, is M2 times acceleration, M1G over M1 plus M2. So this is my tension. Okay, so I have solved the case without friction. But now with friction, what has changed? Now it's just, instead of just the tension, you also have friction, kinetic friction that's acting on M2. Right, so I'm just going to show you the free body diagram for M2. M2 now has normal force, gravity, tension, and friction. Okay, M2, M1 is the same, this and this. So we want to see with friction, is the normal force, is the tension now become bigger or smaller? Because that's what we're trying to compare, right? How does tension compare with the case where there's no friction? It comes down to the application. So let's go back to look at the tension here. Okay, so tension is, because the free body diagram did not change for M1. So with friction, tension M1G minus tension is still going to be M1A. Okay, so tension is always M1G minus M1A. Okay, so without friction, you have some acceleration. With friction, you have a prime, a different acceleration. So all I need to compare without friction and with friction, which one has a bigger acceleration? Because the bigger the acceleration, the smaller the tension, because the tension is something minus the acceleration, right? So the bigger the acceleration, the smaller the tension. So just intuitively, can you guys think about with friction, do you think that both masses will now accelerate bigger quantity or accelerate a smaller quantity with friction?
Smaller.
Smaller, because it's trying to slow things down. So overall, I know A prime is smaller than A. Now, which means if A prime is A is smaller, then tension now is bigger. Okay, so case 2, with friction, you actually have a bigger tension. So the answer to this question is case 2 has a bigger tension. Now, as far as what that tension is, I have already have these free body diagram laid out for you, and acceleration is already calculated, that you can go home and do it yourself. You can see that the holistic view still works. Instead of just the mass 1 is, weight of mass 1 is accelerating the entire piece, it's mass 1 and the friction now is preventing it. So it's like mass 1 minus the friction is accelerating both masses together. So this acceleration is going to be different. It's actually going to be a smaller number that's here, okay? All right, so, but to answer this question, you can think about it qualitatively, that case 2 has a bigger tension. Now let's move on to solving multiple objects. Sometimes you have more than one object, but pulley is still also involving multiple objects, but sometimes they're like right next to each other. So let's look at this particular clicker questions. So I have mass 1 and mass 2. You accelerate them with both the same amount of force. F is the net force that's acting on M1 right now, and give it an acceleration A1. F is the force accelerating on M2 right now, give it an acceleration A2. We know A2 is double the quantity of A1. So when now you accelerate both of them together, what do you get for A3? Now intentionally, there's no numbers. So we have to get comfortable of using these variables. Okay, so take a screenshot of this and again, work within your group for a few minutes on this question, okay? Okay, so 10 more seconds. If you haven't voted already, please put in your choice. All right, let's take a look at this together. I'm going to go ahead and end the poll. All right, so this is what we have for the results. They're kind of quite split between some of these choices. All right, so working with variables can be challenging, especially at first, but once you get more familiar with it, you can see it's actually sometimes it saves you more time. You don't have to plug in numbers. Sometimes these variables actually cancel out. So what is the resulting acceleration? We know that, okay, that means we have to apply Newton's second law. And then on 3 different situations. So we're just going to apply Newton's second law 3 times. Let's see how these relationship work out. So apply Newton's second law on the first situation, F net equals ma, right? M1 A1. The second situation, F equals same F, M2 A2. Now the third one is F equals M1 and M2 together with an acceleration A3. Okay, but we all know that M2 is 2 times of A1. Okay, and these two are equal, so which means M1 A1 is 2 M2 A1. So you cancel out A1. I know the relationship of M1 and M2. M1 is twice the mass of M2, which makes sense, right? You accelerate a bigger mass, you get half the acceleration. You get a smaller mass, you get twice the acceleration, right? M1 is twice the mass of M2. So that's one relationship we got, which can be plugged into the third equation. So M1 and M2 are related. So M2 is half of the mass of M1. So I'm going to replace M2 using M1 over 2. 3. 1 M1 and half of M1 is 3 over half M1 times A3 equals F, right? So compare this result with this result, you can find how A3 is related to A1 because all these answers trying to represent that using A1. So that's why I'm keeping it, I compare with A1 instead of A2. So they're the same mass, so right, so same force, so 3 over 2 M1 A3 is the force, which is the same force as M1 A2 A1, and 1 cancels. So A3 is 2/3 of A1. 2 over 3 A1. So E is the correct answer. You see that we're simply working with our variables without plugging in any numbers. Okay. All right. So I just want to mention that there's some of the content on your current homework may require Newton's third law, and one of the questions is about accelerating in the barrel, like a state fair ride. I do want to touch on that a little bit, but if you still get a question that requires Newton's third law, you feel like you haven't covered in class, I did postpone the deadline for today's homework by 1 week. So you finish that next week, you still get the full credit. So you can simply wait a little bit to do those couple problems. But I do wanted to mention a little bit about the centripetal motion. So let's, I want to go to the slides where at the beginning of the class I showed with this one on your pre-lecture. So when you have a car going in a circle, let's think about all the forces that's acting on your car, right? In the vertical directions, you have gravity here. You must have a normal force to balance out gravity. And because the car is going in the circle, you must have a force that's pointing toward the center that providing this acceleration that is called a centripetal acceleration, right? A centripetal acceleration is v velocity squared over the radius of your circle. So there must be a force to provide that acceleration. So in this case, F net equals ma. The net force is in the direction of your centripetal direction is friction, is m times acceleration c. So friction is going to be m times v squared over r. And where does the friction come from? It comes from your tire pushing on the ground, and the ground will be providing, so your tire has a tendency to slide off, and then your ground will be pushing back on your tire and providing that friction. In real life, your pressure is probably, you're probably pushing on the ground a little bit more, not directly outward, but more like diagonally down and down, more like pushing down this way, right? So your normal force is not entirely equal to mg, but maybe even a little bit more because your tire is also pushing on the ground. But just to, for the sake of analyze this in more clean slate, we just simply say, well, it's just the friction providing the centripetal force pointing toward the center. And we also previously, if you mentioned, you cannot have too big of an acceleration because if your velocity is too big, you're going to require a bigger radius. You're going to slide off. So the person on the barrel question, so I'm going to actually go to that particular slide because you have one question like that on your homework. So for a barrel, rider in the barrel fun, now these people are standing in this barrel. Once they start rotating really, really fast, and you will feel like these people all rise up. They kind of being thrown up against the wall. So they become something like this as illustrated using this little diagram here. So you're like against the wall and your feet is away from the ground of the barrel. So let's analyze the free body diagram of this situation. The force is acting on the person right now. So I'm gonna let you go ahead and vote on this question. And before we delve more into labeling these forces. Okay, I'm gathering most of the votes already. Just 5 more seconds, and then we can take a look at this together. All right, I'm gonna go ahead and close this and let's take a look. This is our results. Quite split between A, B, and C. To look at the similarity between these, we do all agree they all have a downward arrow, and there's the gravity acting on the person. Okay, very good. So we have gravity on the person. And do you think there is going to be any other forces in the vertical direction? Do we have a upward force in the vertical direction? What do you think? Do you think we should have an upward force pointing up? Don't think about what that force is. Think about, do we need an upward force? What will happen if we don't have it? What will happen if you don't have an upward force? What happens if you only have a gravity downward? What kind of motion?
Rather would just fall.
Yeah, they will fall. But this person is not falling. That indicates you must have an upward force. Okay, and this force is indeed provided by static friction. Okay, right. And other than that, now let's think about the horizontal forces. Are there forces in the horizontal direction? Seems like the popular choices A, B, C do agree there is a force in the horizontal direction, but does disagree with in which way it should be pointing at. Now again, let's think about the motion of the person and what kind of motion the person is in. The person is riding along with the barrel rotating. So the person is in circular motion. Very good. Thank you, Eric. It is circular motion. So circular motion is moving horizontally in the circle, right? So for circular motion, you must have a centripetal acceleration, just like the car. And you must have a force pointing toward the center to provide the centripetal acceleration. So because of that, if we look at the side view, there must be a force pointing toward the center, right? That's why the person could do the centripetal circular motion. So you must have a force pointing toward the center. And A is correct. And what kind, so we said the upward force is friction, and this force, what do we call it? Is it spring force, the friction? Is it not gravity? It's not friction. What else?
Centripetal.
Centripetal, yes, it is centripetal. Centripetal is named after its effect, but like what kind of force? We have all these forces. Normal force, yes, this is the normal force, because your person is actually pushing on the surface of the barrel and the barrel is pushing back, providing this normal force pointing toward the center. So A is correct, okay? So normal force in this case is the centripetal force, which is providing the centripetal acceleration. So if you want to write the equation is, so normal force is equal to m equals v squared over r. So that's this case. Someone asked, how is there not a force going to the right? You feel like you're stuck to the wall. That's a tendency of your motion. You are, it's not really how you feel. It's not really like the force is pushing you to the wall. Your back is really closely, that force, you're stuck to the wall, you're actually acting a force on the wall, not on yourself. So you're pushing against the wall, and the wall is pushing back to give you that normal force. I don't know if that explains the question. Yes, you do feel like you're really against the wall, but the effect of that is you push the wall. Okay, the force is acting on the wall. All right, so in your homework is asking, one of the questions is asking, okay, what is the minimum coefficient that's required? So you know that, so this is one, Newton's second law applied one time, right? Newton's second law applied in the vertical direction is this friction minus mg is 0, cancels gravity. So friction has to equal to gravity. And the maximum amount of friction you need is mu of S times normal force equals mg. So you could plug in the normal force and you will be able to find mu of S. So that is one of the questions on your homework. So hopefully after going through this, you will be able to answer that particular question. But if you can't, you can always wait until we finish our class on next Tuesday, okay? So just a little side note, I want to go back to our discussion on the type of Newton's second law applications. There is one last application that's combining dynamics and kinematics. So sometimes here we're just doing F and A, right? The kinematic quantities have velocity, have, you know, delta X, distance. So sometimes it's asking these quantities. So we have to combine these two topics together. So here is one question. You have two vehicles, one M, one twice as much the mass, they're moving in the same direction and speed. They hit their brakes and they begin sliding. Now this is a simplification. In real life, it's you're not sliding, you're really rolling. But just to simplicity, we think they're sliding. So you have a frictional force. That's just the normal frictional force that we talk about is mu of K times normal force, okay? So this friction is applied on both of the vehicles. Which one will stop first? The less massive one, the more massive one, or both of them stop at the same time? We are going back to this question, but before we go back, I want you to go ahead and simply just vote based on your intuition, not to do any calculation, but just your intuition. What do you think? Don't overthink this and simply vote. We will get back to this question later. Um, 10 more seconds. If you haven't voted already, please put in your vote. Okay, all right. I'm gonna go ahead and close the poll and we take a look. This is our results. The most popular answer is the less massive one, to stop first. And remember, this is what we're going to treat is a little bit different from the real life. In real life, your tire is still rolling. In this case, we treat it as a sliding situation. So we use the frictional force in this case. So to answer the question whether which one stop first, we are answering the question regarding the displacement distance, right? So to know which one stop first, we need to know what acceleration. How does the acceleration compare? Because the stops, if you think about this velocity final minus velocity initial equals 2a times x final minus x initial, right? So you can see if they start out with the same speed, this is the same, they both stop, final velocity 0. So this stopping distance is really just going to be affected by the acceleration. All right, so I'm going to change this to another question is, which one has a bigger acceleration, or how do these two acceleration compare? A1 and A2. Okay. So the acceleration require you to apply Newton's second law on it to figure out what the acceleration is. And again, mu sub k is Fk is mu sub k times normal force. So this one I want to let you go ahead and discuss in your breakout rooms. And you can, when you come back, you can vote your answer. All right, 15 more seconds. If you haven't voted already, please put in your vote. Okay, any last minute vote? I'm going to go ahead and close it, okay? Let's take a look at our results. So we have A is most popular. A is twice as much as A2. A1 is twice as much as A2. B is that they're the same. C is A1 is half of A2. All right, so let's go to if you want to figure out acceleration, all we're doing in this current topic, Newton's second law, is to help us figure out the acceleration from looking at the net force. So when in doubt, go to Newton's second law to figure out the acceleration. So okay, let's apply it on both of the cars, right? Applying on the first car, you have friction that's responsible for stopping it on car one is equal to m. M of car one is m times a1. Okay, and what is friction? Friction is mu k times molar force. So friction is mu sub k times the normal force, m times a1. Okay, so what is the normal force acting on a1 car one right now? What is a normal force? Normal force is
M1G.
m1g, yes, mg. So mu sub k times mg is ma1. Okay, so you can see the m cancels out. We don't have numbers, but we can still work on it. We found the acceleration of car one is mu k times g. Okay, you can see that it has no information about the mass in it. You can do the same thing with car two, but you're going to get the same result. If I apply it on car two, I will get mu sub k 2mg equals 2ma2. Okay, so cancel, a2 equals mu k g. So a1 and a2 is the same, that is mu k times g. So my answer is B. To think about this is, yes, that the one is heavier, provided more force to stop, which is this one. It has more force to stop, but it is also harder to stop because it has bigger mass. So the more force to stop and harder to stop, these two effects kind of cancel out to each other and end up with the same acceleration as the lighter car. So if they have the same acceleration, go back to this question, which one will stop first? So the final minus v initial equals 2a x final minus x initial. So remember our vote result from before. I will let you guys vote again on this question to see if we changed our minds or not. Okay, 15 more seconds. If you haven't voted, please put in your vote. The question you already voted once. Now we wanted to re-vote on this. Okay, I'm gonna go ahead and close the vote and let's take a look. this is the results. Less people voted for A now, and the majority voted for C. And yes, indeed, if they all have the same acceleration, the initial speed is the same, right? It all stops. So I'm gonna get 2A times X final minus X initial. So if this is the same, this is the same, and the change in displacement should be the same, which means they will stop at the same time, right? So from here to this to here, it's going to go the same distance, and they're going to go take the same amount of time to stop. All right, so it's C. Okay, so the answer is C.
So with problems like these, where something is sliding, could we treat it kind of like a free fall?
What do you mean free fall?
Well, I was looking at the accelerating truck problem on the homework on number 4, where the box started sliding or something like that, and I was
Right.
having trouble with it. So I guess the only force when something is sliding would be kind of like the force of friction.
Yes, you're right. If it's sliding relative to your surface, you have the kinetic friction. You're right. Mhm. Yeah, so it's like the free fall in the sense that the only force is there's only one force acting on it. So I guess in that perspective, they're similar. I think I understand what you mean. Did I
Yeah,
answer the
that's
question?
yes.
Okay. All right, so that's all for today. For next Tuesday, we will do one more problem on Newton's second law, and then we're going to do Newton's third law. Your homework, you could finish at the end of next week because I've extended the deadline to be 100% credit. All right, so that's all for today. Thank you very much. I'll see you next week.
Have a good one.
Thanks, Professor.
See
Thank
you next
you.
week.
Thank you, Professor.
Thank you, Professor. See you next week.
Thank you. See you all.
Thank you.